Do you want to know how to build a CNC controller from scratch? Or do you even want to build your own CNC mill but are unsure about the controller and the electronics? In this video, I will show you how to consider the controller already at the early design stage of your DIY CNC build, a few guidelines for the overall layout, and the components I have used in my latest build. Hello and welcome to my channel. This is part 6 of my DIY CNC router build series, and the first one dealing with the CNC control. Today I focus on overall considerations. There will be a second video later in the series where I will explain the wiring diagram and the connections of the router to the controller in more detail. In case you haven't seen the first parts yet, where I built the mechanics of the router, I have linked the videos in the description below. When you want to build your own DIY router, or even when you buy a kit, the placement of the CNC controller should be considered from the beginning, because this has already some influence on your machine design, like where do the drag chains have to end, are they running left or right of the machine, and so on. The placement, however, is determined by the available space that you have around your mill. Best case is you have a very large shop and your router or mill can be placed on a movable subframe on caster wheels, ideally welded from rigid steel tubing. In this case, your controller cabinet could be placed under the machine and inside that frame. But in this case, my first advice is do not design and weld the frame first, and then look which controller cabinet may fit into the frame. You will discover that it will be too small. As you can see here, my router will be placed on top of a bench in the corner of my shop. This is far from being ideal, but it is the only possibility that I have. This was already one of the main constraints that influenced the design of the router itself, but it has as well an impact on the layout of the controller cabinets. Below the bench are cabinets with tools and also the air compressor, vacuum pump and other stuff. So the controller cannot go there. And in front of the enclosure is a window, and left of it will be the shelf with my tool holders and end mills. So the only place is actually inside of the enclosure itself. This has the benefit of shorter cable length, but it requires a little bit more attention to the cabinet cooling and airflow, because obviously the air has to come from outside of the enclosure, especially on a woodworking router with lots of dust in the enclosure. But I had the same setup on my previous build, and it worked flawlessly over the years. The only major two downsides are the accessibility of the controller cabinet in case of troubleshooting or later revisions, and again, the available space. The latter is, by the way, one of the reasons why I decided to build again with JMC servos with an integrated driver at the motor, apart from the cost and the good experience I made with them on the previous build. They only require a 48-volt PSU in the cabinet, and you can share the combined power of the PSUs among all of the servos. I also wanted to separate the 400-volt VFD from the 230-volt controller, and in addition I wanted to have the pneumatics for the ATC spindle and other stuff in a dedicated cabinet. So all in all, I ended up with an arrangement of 3 different cabinets, trying to keep the ones for the VFD and pneumatics as small as possible to make the one for the CNC controller as large as possible within the given space. Because out of bitter experience, I can tell you one thing: the cabinet for a CNC controller is always too small. In case you already have a box size in mind for your own build, my advice is take the one which is 1, better 2 sizes larger. Trust me. Having said that, let's have a quick look at my layout. As you can see, I plan the overall layout in my CAD system to make sure that it fits and I don't get any negative surprises during the build. It also helps with the drill pattern for the DIN rails and cable ducts. The 3D models of almost every component you can find on the website of the manufacturer, so this is easily done. I always try to start on one side with the external power supply, in my case 230 volt, and arrange the components in a way that on the other side is the connection to the machine, with the controller signal lines as far away from the high AC voltage as possible. So I have the PSUs on top, then the 24-volt distribution and the relays, then the CNC controller itself, and finally a row of terminal blocks for the connection to the machine. I always connect the wires from the CNC router directly into the controller, routing the cables through cable glands in the cabinet wall. I just don't see the benefit of added cost and effort for connectors, since this combo will stay in place forever. If your cabinet is fixed to a wall, however, and your router is on a subframe which needs to be pushed around from time to time for cleaning or whatever reason else, then removable connectors may make sense, but for me this is not the case. Now let's have a look at the build itself, and I will explain a few things about the components I used. The first task is to mark, drill and tap all the holes to fix the 35mm DIN rails and the cable ducts. Almost every controller cabinet comes with a mounting plate out of 1.5mm thick zinc-coated steel. This holds not only the components, but provides as well a common ground to all the DIN rails on the plate. So in case you build your own cabinet, even if it is out of wood, make sure that you have such a metal plate as a basis for the parts and do not bolt the rails directly to the wood. I use DIN rails and ducts simply because it looks cleaner and makes the whole process more professional, rather than having a zillion cables flying wildly around in the cabinet. Once the mounting plate is prepared, I start to add the components to the DIN rails. I'm starting with the 230 volt inlet. I use these push-in distribution blocks from Phoenix Contact. They are really nice because you have lots of connections on a very small footprint, which is ideal in a confined space like a controller cabinet. They come in all sorts of sizes for different cable gauges, number of connections, and as you can see as well in different colors. The larger ones already have a DIN rail adapter attached, but the smaller ones need to be pre-assembled before you can press them onto the rail. Next up came the PSUs. I have in total 5 PSUs from Meanwell, specifically for DIN rail mounting. A 12 volt, mainly for the fans and maybe some lighting later on. One 24 volt PSU for the controller and relays, and one for the Z-axis brake and air valves. I prefer to have them separated from the controller because of the coil induction. And finally, two 48 volt PSUs for the servos. They can be coupled in parallel and then act as one big PSU. Some people prefer to have one PSU per stepper or servo, but for me this doesn't make a lot of sense. First of all, 4 or 5 small PSUs are more expensive than 1 or 2 large ones. Secondly, steppers and servos have a back current flowing into the PSU when they decelerate. These PSUs can withstand 130% overload. So when you have 1 PSU per servo, that is your margin. But often the motors don't decelerate at the same time. So when you have a larger PSU serving 2 or even 3 motors, and one decelerates and the others don't, your margin is much higher. After the PSUs, I added the relays and the 24 and 48 volt distribution blocks. The relays on the far left are used to switch the magnetic coils of the air valves for the ATC spindle, the tool setter cleaning and the air cooling. Since this router is used exclusively for milling wood, I'm not adding any MQL cooling. Other relays are for the integrated Z-axis servo brake, the touch probe activation, and as a contingency for later functions I don't know about yet. The relays on the right side act as contactors and are for cutting the plus 48 volt line from the servos in case of an e-stop, servo or Spindle VFD error. I changed this arrangement later on to have here as well a contingency for a force axis already built in the controller. In between the relays are the distribution blocks for the different 24 volt supplies, and on the far right are the distribution blocks that couple the two main 48 volt PSUs together. And then I prepared the actual CNC controller itself. I use an Eating CNC 760 control board together with the Eating CNC software to run my machines, and this works perfectly fine for my requirements and needs. The system is extremely stable and I haven't had a single failure in all the years that I used it so far. I know that everybody has its own preference, and especially the Linux guys somehow feel the overwhelming urge to tell everybody that their system is the best and everything else is crap. Well, maybe so, but I couldn't care less. I have a stable system with readily available hardware and do not miss functionality, so full stop. And whether you use a Mach 3 or 4 with an ESS, Linux with a Mesa card, Acorn with Centroid, Masso, Rosetta CNC, or whatever, the layout principle shown here applies to all of them. I started with the Sensor Hub, which is an add-on card that allows up to 3 probe inputs in a wild mix between normally open or closed and NPN or PNP. It comes with a DIN rail mount, which needs to be assembled around the card first. The same applies to the 760 control board. It goes first into the rail mount, then on the rail, and finally I add the breakout boards, which have a lot of screw terminals for the wires to connect. The newer revisions of the aiding boards have already these terminals on board, and as well a couple of built-in solid-state relays, which makes things even easier. Last but not least, I add a total of 63 push-in terminals for the connections to the router. Homing sensors, tool setter, 2 different touch probes, one of them a wireless Renishaw clone, external control panel, e-stop, Z-axis brake, tool change, and the connections to the Spindle VFD Control Cabinet and the Pneumatics Cabinet. I separate each section with dividers for easy identification and added later on a dedicated number to each terminal. And this is the basic layout. From high voltage to low voltage, from power supply to machine interface. Depending on the placement of your cabinet, this can be from top to bottom like here, or when it sits below the router, most likely the other way around. And when the cabinet has to be rotated by 90 degrees, it goes from left to right or from right to left. In any case, try to avoid crossing AC power lines and signal lines from the controller. I will talk a little bit more about EMC and EMI in the part 2 when I explain the actual wiring in more detail. The cabinet for the Spindle VFD is built according to the same principle. By the way, I use these cabinets from Box Expert made out of ABS. The steel cabinet is certainly a better choice, but I actually prefer them over steel cabinets, mainly because they are way cheaper. And at least in my environment, in my basement shop, I haven't had any issues with EMI so far. So first came again the marking, drilling, and tapping, and then the placement of the components. After a quick sanity check of the drill pattern for the parts that go directly onto the mounting plate, I added the DIN rail and the cable ducts first. The main part of this cabinet is of course the VFD. I use a 400 volt 3-phase Omron MX2 with 4 kW and 1000 Hz. It comes with a Schaffner EMI filter and an external brake resistor, which all go side by side on top of the board. In case the cabinet is deep enough, the EMI filter could be oriented horizontally and the VFD could be bolted on top, because it has a dedicated thread pattern for it. And here as well a row with a few relays and terminals as interface for the main controller cabinet and the spindle. I have an ATC spindle and the relays are mainly related to safety features driven by the 3 piston position sensors of the spindle and the VFD frequency. To avoid that the spindle starts unless a tool holder is correctly inserted in the spindle, and also to avoid that you can eject the tool holder while the spindle is still running, just in case you accidentally push the release button at 30k RPM. For the cabinet with the pneumatics, I had to make a custom distribution block first, because the spindle requires different pressure levels for the drawbar piston and the cone cleaning, and I couldn't find any valve island for the Festo valves I use with different pressure levels on the market. If you know any, please mention them in the comments below. After drilling straight pilot holes for the pressure distribution with the machine, I hand drilled them to the final depths. After this block was finished, I could complete it with the valves and bolt it together with the filter and pressure regulator unit to the mounting board, as well as a short DIN rail with a few terminal blocks for the connection to the main controller cabinet. And this is how the three cabinets look side by side, and a good break for part 1 of the controller build mini-series. As already mentioned, in part 2 I will show the actual wiring in more detail. If you liked the video, give it a thumbs up, subscribe to the channel, and hit the notification bell. Stay tuned and see you next.